So we have three different possible structures for thiocyanate that we discovered in the last video. And we discovered that one of them was better than the other two. One of them was not quite as good as that best one, but was still not terrible. And then one of them was really bad. So we had three different possible structures, some better than others. Which one of those is the correct structure? If you were able to shrink yourself down to the size of atoms like Ant-Man and look at the molecule, which one of those possible structures is the actual structure? What would you actually see? Well, the answer to that is none of them. None of them are the correct structure. The true actual structure of the molecule is a hybrid of all three. What you would actually see is what we call a resonance hybrid, where you have a mixture of all three, in this case three, but it doesn't have to be three, but we had three possible structures with thiocyanate. It would be a mixture of all three of those, where the better structures are more heavily weighted in the way that the molecule is arranged. So if you want to think of it in terms of a percentage, if you remember we had the three different structures, I want to say structure number 1 was the second best, 2 was the best, and 3 was the worst. I think that was the way it worked itself out. So maybe in terms of how the molecule looks, it might look something like 75% like structure 2, 23% like structure 1, and 2% like structure 3. Like all three of them have a say in how the molecule looks in reality, but it's going to look most like the most stable structure, like the best structure, but it is not purely the best structure. So because of this, a single Lewis structure won't actually be able to represent the true structure of the molecule. It's somewhere in between. It's kind of like breeding dogs, or really breeding any kind of animal. If you take two different breeds of dogs and you breed those together, you get something that's in between. It's not one, it's not really the other, it's kind of something in the middle between the two. Same thing here with resonance structures, resonance hybrids. So the example here is ozone. So you can have ozone with a double bond on the left and a single bond on the right, or you could have it with a double bond on the right and a single bond on the left. In this case, both of them are exactly the same in terms of how likely they are. You have the same formal charges, and you have the same element, and so one structure is not better than the other. And so the resonance hybrid is exactly halfway between. If you measure the distance of these bonds, and we have ways of doing that, if you measure the length of these bonds, the length of the bond is exactly halfway between the length of a double bond and the length of a single bond. For all intents and purposes, there is 1.5 bonds between each of the oxygens here, which is kind of crazy to think about, but it is true. So this resonance hybrid is a mixture of all the possible structures, where the best structures have preeminence, if you will. They have a bigger say in what the molecule looks like. So how is this possible? How can we have a structure that is halfway between two other structures? How can you have a half of a bond, essentially? Well, the reason that it can do this is going back to the crazy wackiness of quantum mechanics, where electrons are not actually particles held into a single spot. Electrons can behave like a wave. They can be delocalized. They can exist over the entire molecule if they need to. And that is perfectly fine. They can do that. So benzene, for example, you might have heard of benzene before. It's actually a fairly nasty molecule for you to interact with yourself anyway. Benzene is a 6-membered ring with alternating double and single bonds. That's the way that the Lewis structure would work out. So there's a carbon at each of these spots here where the angle changes. And then we're not showing them, but there are hydrogens as well attached to each of the carbons. Um, and so this is how the Lewis structure would work out. But in reality, why would there be double bonds between these and not double bonds between these? Why couldn't those be the double bonds and these be the single bonds? Well, there's no reason why they couldn't be. And so what we see in actuality is that these double bonds don't, the electrons in these double bonds don't exist held between these two carbons and held between these two carbons and held between these two carbons. Instead, because they're just as likely to be in this configuration as to have the double bonds, shifted one bond over, that's just as likely, they actually exist over the entire molecule. There is a ring of electron density over the whole thing, to where, kind of similar like the ozone, we instead have 1.5 bonds between everything in the structure. And so most of the time, if you're drawing shorthand anyway, benzene, you don't bother with the double bonds, you just draw a little ring inside to show that we have alternating double and single bonds, or alternatively 1.5 bonds between each of those. Now sometimes this isn't possible, so if you have your benzene, but instead of it just being benzene, you have something attached to it, like maybe you have a fluorine or something, well then it can get more complicated at that point. So there can be things that will lock the double bonds into place. But if it's just pure benzene, those electrons are shared over the entire molecule. They're delocalized over the entire molecule. And we'll talk more about how these things become delocalized and what these p orbitals, which is what those are, how those play into that later. Alright, let me see here. Don't want to get into those. I think actually I'm going to call it there for this video. Have a nice short video. Because in the next one we're going to do a lot more examples. We'll probably have a video with just examples this next time, because there's quite a few examples here, and I'll do those in a separate video. So I will see you all in the next one.